As you guys know, last class we did number 2 for the entire class. We'll do a little bit more than just one example today, I think, but I thought number 3 would be a good place to go. And so just take a minute and read it over. It's obviously a very short question as far as the intro here. And I want you guys to maybe point some stuff out that you think would be important as far as what we're supposed to do with this. And then once we maybe have pointed out a few of those important things, you have some direction, I'll let you guys try this. And we'll see how efficient you are. There's some opportunities to be very efficient. There's some opportunities to be very inefficient. We'll see how it goes. So anybody see any phrases up there that you think might be key? Okay, we're looking for rectangular equations. So what kind of things will rectangular equations have? Y's and X's, yep. It's going to have X and or possibly Y will be involved here because it's rectangular. Agreed. Any other phrases, words stand out to you as important? All tangent lines? Okay, so let's talk about that. I think that's very important because tangent lines, or did you say all or at the pole, Jasmine? Oh, you said at the pole? Tangent lines at the pole? Okay, sorry. Let's break it down. We'll do it in 2 parts. So tangent lines, what are the 2 things you got to have to write the equation of any line? You got to have dy dx. And what else? For a point, right? You got to have dy dx and the point of tangency. And now let's talk about that last phrase that she mentioned, the at the pole part. What's going on with that?
To make the equation based off of the origin.
Agreed. And the pole is the origin. Yep. Does anybody have any other ideas about, if these tangent lines are at the pole, saying it's going through the origin, right? These tangent lines going through the origin. What might that mean for us? Anything else? Think about the graph there. I don't know. Maybe I don't need to fill in the blank necessarily with that, although, I don't know, we'll see. So we'll see what you do with it. So I think we've broken it down a little bit. Obviously, we've got this r equals 2 sine of 3 theta is our relationship between r and theta. Feel free to graph that on the calculator if you want. Although, did anybody know what shape this is? Maybe you already graphed it. I don't know.
It should be right here.
3-petal? Yeah, the 3-petal rose thing. Yep. Okay, so let's take a few minutes. Armed with that information, see how this goes for you? At least partially make sure that you're on your way, like kind of getting there with this one. And so kind of the most common conversation I've been having has revolved around what exactly does this mean for me? The thing I just circled, what does that mean for me as I'm working on this question? At the pole or at the origin. So maybe you graph this on the calculator. And I'll just do this real quick off to the side. It's that 3-petaled rose as it was mentioned earlier. And it looks something like this, right? It goes here, and sorry for the horrible symmetry, but that's okay, I guess. So it's a 3-petaled rose thing. So guys, here's the thing. When you are at the origin, what is actually going on with the polar graph? Say again? There's 3 angles. It's only 1 point. The origin is just a single point. But there are 3 angles when we're at the origin. What else is true when the graph is actually traced right through the origin? Sorry for the distraction, those of you that are at a certain level. Anyway, come on, think. R is 0. That's the key, right? So when you're at the origin, R is 0. So when you see this phrase, at the pole, at the origin, the key here is to realize that means the radius is 0. And Johnny pointed out earlier that there seems to be 3 angles where that's happening. And what we would do here to find those 3 angles is we would say 0 equals 2 sine of 3 theta, because r is 0 when the graph is actually running right through the origin. Make sense? Let's talk about this with a pre-calc teacher earlier. They were like, do your kids ever solve trig equations? Like, yes, they do. Here's one right here. So you divide both sides by 2. You get 0 equals sine of 3 theta. How do you start getting this theta isolated? What would be your next step? Inverse sine, yeah. So we'd go inverse sine of both sides. So inverse sine of 0 then equals 3 theta. And this is where you kind of wrap around the unit circle as many times as you think you need in order to get all the angles. If you got the graph in front of you, you already know, like Johnny said, you only need 3 of them. But we'll just kind of go in order here. Where is sine 0? 0. Pi. 2 pi, et cetera, et cetera. You could keep going and going. I think after the first 3, I think we've got all the ones that we need. This is where if you kind of know that stuff we talked about earlier, where with the rows, if the coefficient is odd, then you only need pi to get all the way through the flower. If the coefficient is even, you need the full 2 pi to get all the way through the flower, so on and so forth. You divide by 3 and you get 0, pi over 3, 2 pi over 3, and that's really where you could stop, is equal to theta. So these are the angles. And maybe if you take a peek at your graph, can you see how those angles roughly are about where the graph does head right through the origin? I mean, it looks reasonable at least. So the final question then is, now that we know where this graph actually goes through the pole, what's the equation, the rectangular equation of those lines, those tangent lines? So that's what I'm going to leave up to you here at this point. And this would be the place where I would say you could be horribly, horribly inefficient, somewhat efficient, or very efficient at this stage, okay? So, I don't know. I'll leave that part up to you, give you a few minutes to try to wrap this one up. The good news is, we talked about this a little bit, the good news is, for all of your lines, the y-intercept will be what? 0, because we're going right through the origin, right? So that's really good news. You only have to find the slope. Once you find the slope, it's pretty much all over and done with. So I'll let you guys try to work on that a little bit and see how you do. Bold that I think will be really helpful to you. So once you've got these angles, like we talked about, you know the y-intercept is 0. All you really have to do is find the slope. And so if you wanted to, you could do some pretty heavy calculus-y kind of stuff and say y is equal to 2 sine of 3 theta times sine of theta, and x is equal to 2 sine of 3 theta cosine of theta, and then do your dy dx, right? Dy dx is dy d theta over dx d theta. So you do a couple of product rules, and it's relatively painless. So dy dx would equal, let's see here, it'd be 1 d2 plus 2, and then d1 would be, what, 6 cosine of 3 theta? Did I do that right? I think so. And then down here, it would be 1, also would be what, negative 2 sine squared of 3 theta, 1d2, oh, no, that doesn't work, sorry. Let's redo that, because one of them is 3 theta and the other one's not. So it'd be 1 d2 plus 2, and then d1 would be back to 6 cosine 3 theta. Is this making sense to you guys? I'm just going over a few details with this. And once you did that, you would plug in the 0. You'd get something out. You'd plug in the pi over 3. You'd get something out. 2 pi over 3, same thing, right? So let's go over those. When you plugged in a 0, didn't you guys just get a slope of 0? Like a dy dx of 0? So what kind of a line has a slope of 0 and goes through the origin? Y equals 0. So there's your first one. And then the next one, when you plugged in the pi over 3, what'd that work out to be? I don't have it memorized. So root 3. So root 3, which is about 1.73. Okay. So then the next one would be y equals positive root 3x. And I'm guessing the last one would be y equals negative root 3x by symmetry. Okay. You come up with all those, and you're done. So I'd say this is a medium efficient way of doing it. There is a little bit of a faster way that I just wanted to share with you, remind you of a little bit. There was a relationship we looked at way back with when we first started looking at parametric or vector, I don't remember which it was. And the relationship is between the angle from horizontal and the slope. So I'll draw you a little triangle. So if you think about the way lines work, let's say that purple line is the line, maybe like my tangent line that I'm interested in. And then let's say that this red line represents the rise. And let's say that this lovely orange line represents the run. Let's try that again. There we go. And so I've got you can see the purple line is sloping up there, whatever it is. And then right here, this would be the angle from horizontal, right? Theta. So if I continue with this, wouldn't this red line be like a change in y? Or if we're talking about calculus, like an itty-bitty change in y? And this would be a little itty-bitty change in x, right? So let's remember this relationship. How could I relate the theta and the dy and the dx? Tangent. Yep. So tangent of theta is equal to dy over dx. So slightly more efficient way of doing this, and the angle has to be from horizontal. It's not just any angle. It's got to be from horizontal based on the way the slope is written out here. What you could do also, in addition, or different than what you just did, you could take these two angles and just run them through. Tangent of 0, tangent of pi over 3, tangent of 2 pi over 3. You'd get all the same things, right? You get the same slopes. This is only when the angle is from horizontal. I can't stress that enough, because what some people will do, and I get it, they'll be like, oh gosh, are you serious? So that's the relationship? Why do we even bother with this ever? Because that's a lot more complicated than just doing the tangent of the angle. Again, let me repeat. This only works if we're talking about the angle from horizontal. It's not going to allow you to find the angle of some tangent line, way if you've got some looped limacon that does this or something. It's not going to allow you to find the slope of the tangent out there, right? It's only from a horizontal relationship. So don't get too wrapped up in, cool, I'll just always use that. Well, then be prepared to miss most of the questions. Okay? Colin. So this one is really straightforward to me because we're talking about at the pole.
So if it's not at the pole, then it's
we can find some exceptions to that, but for now, let's just say yes. Yes. We can definitely find some exceptions to that, but for now, let's just go with what you said. I think that will be the most helpful. Okay. So how's it going? Tangent lines at the pole, we good? Okay, so we're going to shift a little bit here. I do want to point something out to you real quick, that at the end of your notes, kind of like we had before with most of the stuff in the first semester, when you get to the end, there is some extra practice-y stuff, and I obviously have my answers up there, whatever. So you'll find some other good examples in regard to what we've been doing that you could practice with when you're thinking about a quiz or a test later.
Mr. Anderson,
Yes, ma'am.
did you intend the answers to be there?
Oh, did I post that? Well, I don't really care. It's just extra practice. Did I not post one where they're empty? Oh, I'll do that. Sorry, I must have posted the one with just the answers. Yeah, my bad. Okay, thank you for pointing that out. Okay, so we're going to shift gears a little bit. We are going to continue talking about calculus, but instead of talking about tangent line equations and vertical and horizontal tangents and slopes at the pole, we're going to be talking about area. Okay, I hinted at this a little bit earlier. So when finding the area under a curve using rectangular coordinate system, we used a lot of different shapes, but what was kind of the main shape we focused on with those? Rectangles is pretty much always that. So rectangles was the shape we used to help us approximate the area and kind of build towards those Riemann sums and finding the actual area. I mentioned this last week. If we're dealing with a polar curve, we will not be using rectangles. We will use blank Sector, yep, it's like the little part of a circle. We use sectors to help approximate the area and then kind of lead us into using the definite integral. So I thought that how do I want to do this? Let's do this. I don't know. I feel like there's always at least one person in the class that like has these old geometry formulas memorized. And I don't know. Does anybody know the area formula for a sector? Is it SR?
S equals
What is-
theta R.
SE? Oh, like S. Not, what does S stand for?
Sector.
Sector area? Or
I think it's in my calculator.
you are? I think you're talking about arc length is what you're getting at.
Oh, that might be it.
So, hey, Josh. Whatever you do, don't look it up on the calculator and just like spout it off because anybody can do that. So my thought is, let's develop it real quick. Maybe this will help you remember it. So if I were to just draw out some random circle, what's the area formula for just any circle like that? Pi r squared. So there's the center, and there's a representation of the radius. And so you'd say area of a whole circle is pi r squared. Okay, so then if we're finding the area of the whole circle, that's no big deal. You plug in the r and it's over with, right? But what if we are not finding the area of the whole circle? What if it is just a little part of the circle, like a sector, like that? So we're trying to find this this orange area, or we could find the larger white area off, like the bigger part of the pie, if you will. We could find either one of them. Any ideas on what I could do to find that? It's obviously part of a circle, but what part is the question? Theta over 360. Okay, so theta over 360 times pi r squared. Now, what's theta measured in? Well, the way that you have it written up there, what is 360 in? 360 is in degrees, so theta would have to be in degrees. Okay. So as you know, in our class, we don't typically use degrees, although what you've got right there is totally right. How could we convert this over to radians? Theta over 2 pi, right? Because the whole circle would be 2 pi radians. So it would be theta over 2 pi times pi r squared. And then we got a little bit of cleaning up we could do here. Obviously, you can see that the pi's cancel out. And just left with that over 2 out there. So the classic way to write this is 1/2 times theta times r squared. So that right there, the thing I'm putting in the orange rectangle, is the area formula for a sector. So if you know the angle size of the sector and you know the radius, you'd plug the two in and you'd be done. That make sense? Okay. So then, how is this used in calculus? So let's make something up. Let's just say we've got, a cardioid. That's actually a pretty good half of a cardioid. I'm really nervous about this other half.
Just copy it and then you.
Oh, it was going so well.
What?
I'm gonna be happy with that. I'm gonna choose to be happy with that. So the challenge here that shows up when you're trying to find the area of maybe something like that is that the radius, at least on 1/2, is never the same. And of course, we do have a mirror image going on here. We do have symmetry, but if you think about the radius from here to here, it's whatever length it is, and then it's longer there, it gets longer and longer until we're down here, and then it starts getting shorter and shorter on the other half. So the radius is constantly changing, and so this is not a circle, right? Newsflash, not a circle. So we can't use just a circular type formula, or even just the sector alone to get this. So the thought here, mentioned this in a last week, if I could divide this up into sectors, maybe it would be this little sector here, and then then another one over here. It's got that nice curved end to it. And then there'd be another one over here. Maybe you can start to see that these sectors would actually be a reasonable approximation as I build those out for the area. Sort of like the rectangles were a decent approximation for a curves area. These would sort of fit in there. I could keep going, but can you see how this would be sort of like one of those Riemann sums where in the end you can look at it and say, well, sure, it's pretty close, but I can see some little places where it's too large or too small, and there's some overhangs, and there's some places where it didn't quite get, so my approximation is truly an approximation. It's not exactly right. Sorry. So then what would I need? What would I need to do to get this approximation better?
Make it in
Yeah. What would I actually be making as small as possible? The theta, the angle, right? So what did I divided this up into what? 1, 2, 3, 4, 5, 6. Bless you. 6 sectors over on the right. So the idea is, what if I made the angle smaller? Wouldn't I be able to fit maybe like 12 sectors over there? And if I made the angle even smaller, maybe I could fit 100 sectors. That'd be even better. And Josh pointed out, we're looking at an integral. I'm sure you all see that as well. Because how many sectors do I really need? Yeah, I need an infinite number of them, because then the angles would be squeezed down to almost 0. And then I add all those up. The only way I can really do that is with a definite integral. So you can see it down below there. It's kind of right on the edge of the board. In order to actually find the area, I need to do a definite integral. Let me just move up here. I need to do a definite integral involving that sector formula. And by the way, I honestly don't think I can say this enough times, because sometimes I think we feel like this is magic. If I've got rectangular coordinates, do you guys remember that the area is the integral from a to b of f of x times dx? Let's remind ourselves of what that actually is. What does f of x stand for on the graph? It doesn't stand for area of anything, sort of a length. Say again? The height of what? Height of a rectangle, yes. And then what does dx stand for? The base length of the width, yes. Of a rectangle. And so way back when we did the definite integral from a to b of f of x dx, all this was right here was just base times height, or height times base technically. And so maybe it doesn't seem that ridiculous when we look over here at the right and say the area of a polar graph, or part of a polar graph, would be 1/2 integral, and then it's not an a and a b anymore, it's an alpha and a beta. So this is going to be an angle, and this is going to be a different angle. So it's the area between these two angles of r squared d theta. So you can see that 1/2 r squared theta formula coming into play. So are you making connections here? Is this making sense?
Yes.
Math should make sense. If it doesn't, we got a little problem. Okay. So then let me draw down here just a little bit on this, and then we'll do an example. Yeah. So let's go back to this. I'm going to try take 2 on the cardioid, see if I can do even better. It's probably not going to happen. Whatever, okay. So let's say that we had to find just the area of part of this. Maybe it said, let's find the area from, let's say it said find the area only in, say, like the 3rd quadrant. So it would be from here, sorry, let me do this a little better. It'd be from here to here. Let's say we were only looking for that area right there. Or 4th, did I say 3rd? Let's say it's 4th. Okay, so if we're trying to find that, the way I'd set this up is, all right, it's going to be 1/2 integral, and it would be r squared or f of theta squared, whatever that is. We'd need a an equation for that times d theta, what would you guys guess the alpha and the beta would be? 3 pi over 2 to 2 pi. Sure, that works. 3 pi over 2, which is pointing straight down, sweeping out the area all the way over there to 2 pi. That would give us that orange area. Sir.
Wouldn't it depend on the R equation? Because some things are like pies and things are 2 pi.
Yeah, sure. That's definitely a good point. But if you think about it, if all I'm looking for is just a little part of it, I actually could have, like, the angles could go crazy, right? Instead of like 3 pi over 2, couldn't I just add a full revolution to that? And this would be 7 pi over 2. And then I'd add another full revolution, and this would be 4 pi. That would give me the exact same area. Like that thing we talked about earlier, how there's an infinite number of ways to get to the same point using polar coordinates. If you wanted to be really weird, you could add like 19,000 revolutions onto both of those, and you'd still be correct, right? You'd want to be careful because you might, in all of your calculating, you might mess up, and now it's wrong. And now I'm mad because you made me count, and you're wrong too. You know, if you make me count and you're right, I'll just laugh, whatever. But if you're wrong too, like, come on. Anyways, so do you see how the alpha and the beta come into play? They are not x's and y's. They are angles that the sectors kind of sweep through. Visualizing this okay? All right, well then let's do an example. Flip ahead to that next one. Let's see how you do. So example number 1 says, find the area of one petal of the rose given by r equals 3 cosine of 3 theta. I gave you a little graph there. If you want to graph it, you're welcome to it. You really don't have to have the graph to do this. Like ever since you guys were in like 7th grade or 6th grade or something, you've been graphing with x's and y's, and so for the most part, you're like very good at just about any x and y stuff you might see. R's and thetas you've barely done, relatively speaking, right? I mean, it's very, very small sample size. So I totally get that you would look at something like this and say, I'd really like to have a graph. I'd really like to have a calculator. Could this question in this form ever be on a no calculator part? And I'll say yes with a caveat of the finish would be tough, like we talked about. And I don't think I have you finished. But as far as setting it up, definitely you'd want to be able to set this up without a calculator. The next question would be, okay, I see that it mentions that it's a rose, but then how am I supposed to know exactly how the rose goes? Am I supposed to like plot out all the points and figure out, is it like this or is it like this? Or, how's it go? What am I supposed to do? Here's the key thought. Big takeaway. Whether the rose has 2 petals, 3, 4, 6, 8, 10, whatever it is, however many petals the rose has, where do all the petals start? Origin, when what is 0? Radius. Whenever radius is 0, that's when the petals start. I mean, I look at this and I see, find the area of one petal of the rose curve. So I look at that and I think to myself, I know that it's a rose. And I might not even necessarily have a clue about how many petals it is. I might even mess that up. I might say, oh man, at 3 theta, does that mean there's 3 petals or 6? I can't remember. You know what? It doesn't really matter. All I need to know is that the petals start and stop at the origin. And if I know that, I know enough. I might be feeling insecure because I might be thinking, are there 3 or 6 petals and what does it look like? It'd be nice if you knew that. It'd probably be a little more helpful, but you don't have to know that. Here's what I would say. Since I know that the petals start and stop at the origin, I can start to get a sense of this if I just set r equal to 0. Start to get a sense of like, all right, how many petals might there be and where do they start and stop? Even if I don't know exactly what the graph looks like, that's what I would do. So I'd say 0 equals 3 cosine of 3 theta. And of course, that means that 0 equals cosine of 3 theta. I do the inverse cosine, blah, blah, blah. And I'd get 3 theta is equal to inverse cosine of 0. So for what angles is cosine 0? There we go. Pi over 2, 3 pi over 2. And I'm going to get several of these here because I want to make sure that I'm getting all the ones that I need. Wouldn't the next one be 5 pi over 2? Okay, so 5 pi over 2 and 7 pi over 2 plus dot dot dot, or should be comma. They all equal 3 pi. Therefore, my angles would be like pi over 6, pi over 2, 5 pi over 6, 7 pi over 6, dot, 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 equals theta. All right, so let's start to think about how many radians are between each of these petals. So I've got pi over 6 to pi over 2, pi over 2 to 5 pi over 6. Well, let's see here. Start to plot this out a little bit. So pi over 6 would look something like that. Pi over 2 would look something like this. 5 pi over 6 would be about like that. Should be some symmetry there. 7 pi over 6 would be here, like so. I'm starting to see this. By symmetry, couldn't I probably throw one of these in there too? So it'd be, there'd be one right here too, wouldn't there? There'd be a 3 pi over 2.
Do you, so like, when you originally do the inverse cosine of 0, you have 3 pi over 2 as one of the angles of that. How do you know?
Well, I divided by 3.
Yeah, I know that. So those are the actual thetas of the function. How did you get that 3 pi over 2 is one of them? I mean, that would.
Well, I was just taking this here. Let's fill out the rest of it. So it'd be 9 pi over 6, 11 pi over 6. Oh shoot! Sorry. Hang on. Let's go back up here. This is where I want to be. So it'd be 9 pi over 2,
Yeah, I see.
11 pi over 2, so on and so forth. And I think that would get me all the way around the circle once, right?
9 pi over 2 would be your.
So then 9 pi over 6 would be 3 pi over 2, and then it'd be 11 pi over 6. Okay, so you still might be questioning this and saying, well, gosh, I don't know exactly where the petals are. You could even plot a point here, right? I'm basically assuming that you know almost nothing about the graph of this, other than that it's a rose, right? So the question is, are the petals going to be, obviously this makes a difference, are the petals going to be here, like that? Or is the petal going to be right there? Because that would make a big difference as far as which angles you use. Does that make sense? So, any ideas on how you could figure out exactly where it is? Come on. We only got 3 minutes. We don't need many of them. Yeah, just plot a point and see what happens. I like the idea of plotting 0. So if I plot 0 and I end up with an actual point in there, then I'm going to know that that's where my petal of my flower is. So plug in a 0, don't I get 3 cosine of 0? So I'd say this is, this would be one end of the petal. I could plot some more if I wanted to, but I think that I'm going to find eventually one of the petals is right there. Does that make sense? Plot a couple of points. Again, I'm assuming that you know almost nothing. And if you know a little bit more than nothing, you probably could do a little bit better and faster than this, right? If you know a little more than that, you could probably be even faster than that. So here's my thought. I'm looking for one petal. So how about this? Here's one idea. 1/2 integral of 3 cosine of 3 theta quantity squared d theta. If I want to go from here to here, what's that lower angle? I want the negative pi over 6, right? If I put 11 pi over 6 in there, I'm going to be going the wrong way around the circle. So negative pi over 6 to pi over 6. That'd be one way to do this. Did anybody do this? Does Some people were asking me about this. What's that based on? Isn't 0 to pi the whole flower? And if I just throw a 1/3 on the front, don't I have 1/3? I got to know that there's 3 petals though, right? That's what I'm saying. That the way I showed you would be if you know almost nothing about the graph. If you know that it's a 3-petaled flower, can't you just do the full period divided by 3? Done? That'd be even easier. So it is helpful. Like the more you know about these polar curves, the easier it could be for you. But if you know nothing about them, you still can navigate through and get the angles right and get everything set up. At this point, it would be calculator active, right? We're not going to be doing the cosine squared of 3 theta on paper and pencil. We'll do it in the calculator. Liz, your question?
How would you know that there aren't 6 petals? Like
Well, there's a lot of levels to that, answers to that question. The first one is, like, if n is odd, n being the coefficient on theta, if n is odd, then the number of petals matches n. If n is even, then the number of petals is doubled. It's 2n.
So,
You guys are good to go. Have a wonderful rest of your day. I'll see you tomorrow.
but like if you were drawing it from the dotted lines, how would you know that there's not a petal? Like if, say you didn't know the even and
Sure.
odd.
So let's see here. If you plot points, right?
Yeah.
So let's see here. So like pi over 4, let's just see what happens. So pi over 4 would be like, thank you, see you later, have a good day. Pi over 4 would be like up there, right? So if you plug in pi over 4, you would get 3 cosine of 3 pi over 4. And 3 cosine of 3 pi over 4 is negative.
Where's the blue?
Cosine of 3 pi over 4. So that means actually, even though you're pointed this way, you'd be putting down a point like here.
Thank you.
And then thank you, see you guys. And you'd find out that this actually does this.
That's so weird. Oh, okay, and that's why it only needs pi because it.
Yeah, you start getting a bunch of negative radii as you circle through.
Okay.
Yeah, so you'd get that. And then if you started plotting points up here, you'd get to here.
Yeah.
My scale's off. Or no. Sorry. No, that's not it. You start plotting points, you'd get up here,
Yeah.
like so.
Yeah.
And then if you kept going around the circle, you just see it repeat, right? So you'd see that, oh, I'm just putting more points down where I already had points down. At some point, you'd be like, all right, there's only 3 petals because I just keep retracing it. And that's where, like, the more familiar you are with it, there's gonna be less of that, like, oh my gosh, is it 6 or 3? And what does that mean? So, and we're practicing it. You'll get a little more practice. You'll get better at it. Thank you. See you guys. Good job. Have a good one.